Can I start? Okay, so I am doing problem 4.513, which is a simple beam that has a distributed load and also a concentrated load, and it asks to find the shear force and bending moment diagrams for the structure. So start off, I define my coordinate system as this is positive y, this is x, and going just as positive moment. And then I drew the free body diagram, which this is a, y. Oh, and I assume that since the problem did not give me a mass, that it is negligible compared to the forces, and that it is a rigid body, and that it is in like static equilibrium. So then I can assume the free equations is true. And this and the pin on the left doesn't have roller, so there's an AX and an AY. And for B, since they can move in X direction, there's only AY. So then now this is like this. Oh, this, and we're given that, yeah, this is L/2, or this is just like 1, and then this is B, Y, this goes up, and that in the middle here there's a P down, and from like just derivation, know that the centroid of triangle is 1/3 in from the figure side. So then this will be from here to, I guess, 1/3 will be the W. So now to find W, since we're only given Q0, do kind of like the area, which is 1/2 BH, in which case like the height is the load given. So then there is 1/2 times 1 meter. And then oh, this is 1.3 because it's 1 meter and then 1/3 from, oh wait, no, oh sorry, the base for this, yeah, is 1 meter because it ranges from here to here, from the middle to B, so that this is the force. So then now, since we said that we assume equilibrium, we can use the equilibrium equations. In this case, there is nothing going on, so AX is 0, and in order to find Y, first need to find do the sum of moments at A, because at A is more convenient. We're just finding these three. So then we have By 2 meters from A minus, and is positive since this we said this is out of the page is positive, and these two will be negative. So that's why the minus 1 meter minus W 1.33 meters equal to 0, and this becomes 2 meter Y minus 350 Newton times 1 meter minus 875 Newton times 1.33 meters equal to 0. And then solving for By, and then since it's Newton meters, but there's a meter here, it divides, the meters cancel out, so it's going to be newtons. And going to be 758.33 Newton. And now we have By, we can use it on the other side to find the forces, which is adding this and minus the two forces, and plugging it in is, we have this, we set to be 758.33 newtons minus 350 minus 875 newtons 0, and so then this equals 466.67 newtons. So there's now this and there's that, and so then we can use the Q naught and like W and these to make the shear, to find the shear and the bending moment. So, and since in the first section, since they kind of divided it, in the first part there's not really like any force until the middle, and then there's another. So then I kind of split it from 0 to 1 and 1 to 2. So then for shear, from 0 to, yeah, that we know the shear is just, since if you split it, there's nothing, there's just going to be a y. It is just going to be the same as the 466. And that at because this is non-inclusive, so not here, but then at 1 meter.
For each range, you need to draw the free body diagram.
Okay. So this is just going to be y, and ax is already 0, and this is not quite to 1, but I guess just x, where from 0 to 1, and so what was I? Okay.
That has to be equilibrated.
Oh, and then there's a I guess a reactionary like force down. So I guess just C and CY.
That's the
Oh,
shear
yes,
force
P.
that you're calculating.
Yeah.
So it's V.
Okay. C A. Okay. So then
It takes care of the force equilibrium, but not the moment equilibrium.
yeah.
Left by themselves, this
Yeah.
will keep rotating.
So then it is going to be just a couple this way, and this moment this way. I think a moment that way as well to balance it out.
So those are the two things that you're going to find out.
Yeah. Where was I? Oh yes. So but then at 1, at x equals 1, since there's a p downward, minus the. So this is from 0 to 1. Should I draw another one for just at 1, like at that point?
Come again?
Should I draw another the diagram for just
Not necessary. Wherever the force changes,
okay,
or any loading changes, or there is a new support, then you have to go draw a new free body diagram.
Okay.
But all the way from x equal to 0, that is the A end, to the middle, which is 1 meter, you don't need more than one free body diagram.
Okay. Yeah, so then this is going to be what this is minus the force P, which is 355. And so then this we now know like the jumping point from here till when there's a force applied. And then to finish off, so I guess on the other side to do this is I guess kind of split in the middle. This is from 0 to 1. And to finish here from 1 to 2, suppose the diagram would be like this. EY. There is a shear, and then there's also, just the name this way, a moments that way to counteract it for B. So then to find out this, I took the what we have up here, and since it's like sloping downward, I just like the point slope form found a slope which is like 0 minus this over the x interval, which is 2 meters and 1, and this is just negative 50, and then I use this to find, since it's from x to 2, it is q of x, or I guess w is from negative 50 newton. Oh, this is newton meters. X minus 2m, which then I just distributed negative to move this up front. So then I had this. So then afterward, I integrated this, since this is the the derivative of like is equal to negative w, or like q of x. So then v is going to be the integral of negative dx. So then I found it and did this integral from 1 to x being 2, and since like this is x already, I just changed it to like ds and s so that I can do it. Then it is going to be there's the negative from there, 1750 newton meters 2m minus s ds. And since we know that this begins at 1, and at 1 we already found that the shear is going to be 116, I added the, I guess this is called like the boundary condition, or like the initial condition, kind of like the plus c afterward. And I'm just gonna write out the what the integral is over here, which this now is v of x. That's 875 Newton. All of this is in newtons. 350,271.7 newtons, whole thing. And then to find out the shear to verify, because we know that the shear at B should like be the same because of this free body diagram. If we plug in 2 here, we get negative 700 and just this, which is the same as this one, but since B is positive, this like now it verifies that our equation is correct. And for V1, if you plug in is this up here, which also holds, as we stated, that it's going to be down. And finally, to find out what the maximum, or for later to find a maximum moment, we need to solve for this when v of x is 0, because that's when there's a sign change, and that's like the I guess the derivative rule to find like a maximum or minimum. And solving for when this is 0, x is 1.07 meter rounded. And now that we have this and the other stuff, we can integrate again to find.
So what you're solving there is a quadratic equation.
Yeah. There's 2 solutions, and then one of the solution is I think 2 point something, but then that is outside of the wrap bound of the beam, so that it doesn't matter. So I only took one of them instead. And now for a moment, from here again, for this, it is just going to be like from ax from taking the moment here is going to be ax times the distance x, and that is just going to, and since like at 1 is x is just 1, so it's just going to be the same as 466.67. So I guess 1 is going to be this Newton meters, and that is just from the peak up at that, and we know it's going to be increasing from when this is 0 going all the way up to the middle. And for this side, we integrate this again, but now this time we have the starting condition like the same boundary as this, because we know it picks off at 1, and I'm just gonna write out the answer. 2,167 cubed minus 5 squared. 860.67 meters. And then from there, just to check, plugging 2 for this yields 0 at this point. There's no moment at B, which makes sense. And then to find out the maximum, we use the quadratic solution earlier to plug it back in, and it turns out that m at 1.07 is equal to 470.68 Newton meter. And now to actually draw the diagram, since we have all the numbers for shear, I guess I'll draw here. We know that it starts off, it is for this side, it is consistently 466.67. So 467 newtons, and that goes all the way. This is going to be 1 till it is 1, and it is going to drop down by at 1. It's going to drop down by P, which is 350 newtons, and then then it's going to subtracting 2 is going to become 116. And then from here, it is going to curve downward with like the quadratic till to negative the shear for B. I wrote it somewhere. It's going to be negative 750, and it is going to cross, since we said this is one of the x where it is 0. It's going to at 1.07. It is going to cross 0, so something like that. And this is going to be negative 758.3 newtons. And then at B, it is going to go back up to 0. And then
what type of curve is it going from 1 to 2?
A parabola, quadratic down, right? I think.
Look at the load. Look at the load. Look at the diagram.
Oh, the diagram?
Load diagram. Then you will know this way.
Is it not quadratic? Or
you also have that equation we have written there, dv by dx equal to minus w, right?
Yeah.
So what kind of behavior would be v versus x? Because you know the behavior of w versus x.
Yeah.
W versus x is a...
Wait, what do you mean? Sorry.
How is w varying with x?
Oh, it as it increases, it decreases. So
yeah, but is it linear, quadratic, cubic?
Oh, linearly decreasing?
Yeah, it's linearly increasing with x. Right?
Yeah.
So then if you integrate, what would v, how would v vary with x?
It'll be...
In fact, you've done all the integration, so...
Yeah, it'll be like, find the area...
So you have that v of x there.
Yeah.
You have an expression already.
Right.
So, so how is it varying with x?
It's quadratic?
Yeah.
Oh, it's upward?
That's it upward or downward, yeah.
Yeah. Oh. So it'll be go up this way?
The quadratic can be this way, or it can be this way, right? So
I see.
So no, don't take my word for it and erase it.
Okay.
You might be right. So I might be playing the devil's advocate.
Oh, I see. I see. Yes, this is positive. I see what you mean. Okay, that will make more sense. I see. This is kind of far apart. Assuming it is like closer, like that. And so for the moment, it is the same. Said somewhere the bending moment is 460 Newton meters, and it increases linearly to this point. So like that, and this time it's cubic.
Checking on the numbers.
So it'll be like this, yeah, and it hits the max from like this is 470.68 at max, and it will go down and went to 0. Wait, yeah, it's like cubic, I think. Yeah, on my drawing I swapped both of them to down, and the sign is wrong, but I think I fixed it. And this is at 2, and this is 0, and I think that's it.
Just think about the moment diagram.
This is a slope.
Even, can I help you?
Yeah.
Here also. Look at this. This is almost a straight line. This has to end like this here. It goes like this.
Yeah.
It's
More curved. Yeah.
no, from here you can derive this.
Yeah. Okay, so since this is a slope, then the slope is going like that. It's negative, so it's,
You also draw
okay,
the, just above that, you draw the W versus X.
oh, should I draw it like somewhere?
Yeah, just draw the W versus X. Then you can compare, you know the derivatives there.
W versus X is like down, like from 1 to 2.
Yeah. Right.
So this is the first, and then the quadratic, it's going up.
See, what is dV by dx in the V versus X curve? It's the slope of the curve.
Yeah.
Right?
Yeah.
When you're plotting V versus X,
this is
dV
the
by
slope
dx will
of
be the
this,
slope of the curve.
right?
So just for the quadrant, see the constant portion.
Mm-hmm.
What is the slope of the V versus X curve?
466 points different.
What is the
for here?
in this shear force diagram?
Mm-hmm.
What is the slope here? Zero.
0.
Right?
So
because
that,
it's constant.
yeah, it's constant here.
So constant. So from this, can you say something about W there? Because dV by dx is 0.
Mm-hmm.
So W is
0.
also 0.
0. Oh, yes.
So you know that in the problem W is defined as 0.
0.
So
yes.
you can cross verify that.
Oh, okay.
Okay. So that's the trivial portion.
Yeah.
Okay? But then you can go one step further. Just like your dV by dx equal to minus W, you also have dm by dx.
By dx is equal to v.
Very good.
For
So,
this.
yeah.
That's the y. The
Right,
slope is
right,
1
right.
because there's that one that
Correct. So this is what kind of a curve is this?
linear.
Linear. So
line,
its
yeah.
slope is
The 600.
yeah. So it's constant.
It's constant. Yeah. Oh, yeah.
Right. So that's if the slope is constant, then dm by dx, which is v,
Yeah.
should be constant.
A line. Yes.
So you verify that the slope of this is constant, therefore it is constant here.
Mm-hmm.
The slope of this is 0, so therefore it is 0
0
here.
here. Yeah.
Okay. Can you make a same argument about the second half of the v?
Yeah. It's negative going
Start
down.
from the bottom.
Oh, start from the bottom.
Okay. So you have got all of them. You just want to verify just if it's okay. So what kind of a curve you have got for m versus x in the second half?
Well, it should be a cubic. And if it's down.
See, all that you're bothering about is the slope here.
Yeah. Okay. So.
Okay, so is the slope increasing or decreasing?
The slope is a lot in the start and it's decreasing.
The slope of the the slope of the m, correct.
Yeah. The slope is like a lot at the start and it's,
x.
and it's like it decreases as x increases.
Good. So it
that
starts
is,
it starts with a positive value.
Yeah.
Keeps on decreasing to
this,
what? No, just let's stick with the m versus x.
It decreases to 0, I guess.
Yeah.
It stops moving at the end. And
so what is dm by dx? It is v.
Yeah. So,
is it showing there?
Yeah, because this is negative. So this is a slope. So it's wait. Now I'm confused. Yeah, because this is negative and it's going more negative.
No, the slope of the m curve should be v. Slope of the v curve should be w. Right?
Yes.
So go from the bottom.
From here?
Yeah. So in this curve, see what we have is dm by dx.
Yes.
I want to make sure that it is really
okay.
So I start with the slope.
Yeah.
What is the slope here, and what does the slope become here? The way it is drawn.
I guess a negative slope.
So if it becomes horizontal, it is 0.
Yeah.
But is your shear force 0?
No.
So one of them is not right.
Right. Ah, I see.
So it's your own self-check.
Okay.
It got
Did you understand what I said?
I think like, but I don't know which one's wrong. I don't know which one's wrong.
That's the best part.
Would it? So this is not 0. I'm not really sure. Can I go sit down and check?
What about the values? See, your m is going to 0 there, right?
Yeah, yeah.
So that from your boundary conditions, you know is correct or wrong. So what are the boundary conditions? Simply supported, right?
Yeah.
So both the edges are on hinges. One
Right.
on rollers, one without rollers,
Yes.
right?
Yeah.
So on hinges, you can never have moments unless you apply it,
Right.
right?
Yeah.
So no moments are applied in this
Yeah.
problem.
And then yeah.
So you should have moment equal to 0, right?
Yeah.
So which
is
you are
okay.
getting correctly, right?
So this is
So the
correct.
value is
and this
correct.
is
No. The
Oh,
value
okay.
is correct. Just the value at the
so the
right end
graph.
is correct at 2 meters.
Okay.
Right? Similarly, your shear force, because a hinge can provide a vertical force,
Mm-hmm.
right? So it is non-zero, right?
Yep.
So you're having a non-zero value there is fine. Okay?
Okay.
So the values themselves are fine. You're only worried about the shape of the curves.
Mm. Would it? That way.
That's
Or
why I said-
this way?
Okay. You see the way in which the slope of the curve of your shear force going. Every time you draw a tangent, divide that into some, let's say, some 5 points. Starting from 2, you have written 2, no?
2. Okay.
No, 2. You at the corner, at the boundary condition,
Oh, 2.
2.
Okay.
Divide it into some 4 sectors.
Sorry.
4 sectors. 1, 2, 3, 4, like that.
Like here.
No,
Or
not
parts.
like that. That's not sectors.
Sorry, I don't know what you mean.
Don't shake your hands. Be confident. Here, 1,
Oh, I see.
2, 3.
Okay.
Now, each point you draw a tangent like this
Mm-hmm.
and see how the slope of the tangent varies. And then you
Oh, okay. So if this is that, it is becoming more and more. The slope is becoming more and more 0 for both, because then like here will be 0, and this is a stronger higher slope.
the tangent has to be, see, when you draw a tangent, it has to be perpendicular to the sectored line that you have drawn.
Yeah.
I have not drawn it correctly. Oh, yeah, like
Here.
that.
Yeah, like that.
Now you can measure the variation of the angle and imagine how does it fit.
What do you mean? How does it vary?
See, it's this equation that you're
Yeah.
thinking about.
Uh
We
huh.
have a W here.
Uh huh.
So this is the slope of your V curve. V versus X
Yeah.
curve. Slope is dV by dx.
Okay.
So that slope should agree with W.
Okay.
You know that at that where you're starting
Sure,
in the
yeah.
middle of the V,
Yeah.
there is a positive
Plus
slope.
slopes. Yeah.
Then the slope slowly comes down
So-
and becomes zero.
0.
Right.
Okay. Oh, so it's a negative.
Is it showing there?
No.
Is it becoming
No.
zero
it's-
there?
it's
Is
not.
it positive there? That's
None of the slopes are positive. They're all negative. So it would be.
So can I give one more clue?
sure.
This will
So there is a negative sign. Sorry, there is a negative sign.
Oh.
see what
Uh-huh.
is the slope of this?
0.
What is the slope of this?
Infinite.
This line.
That like.
This is
1.
0.
Yes.
If this is 0, what is this?
That the vertical line.
Huh.
Infinite. Yes.
Slope of this is
0.
0. Slope of this is
1. Infinite. Isn't it? If it's vertical, it's
okay. If this is minimum, what is
Uh-huh.
this?
maximum.
Okay. Now you draw this. Yes. I mean, all that Prof is doing is that he should imagine and he should derive it on his own. Then the fun is more for him only. Yeah. That's why he's not taking that.
Any of you want to help? Yeah,
Yeah,
please feel free. Yeah.
So is it just that the blueprints like this? Because he is the
Right, but you need to walk us through the logic.
Yeah.
It's not just guessing here.
So his V graph is correct. His V graph is correct, but instead of
You have to go check one by one, because otherwise we will assume something wrong is correct, then what follows will also become wrong.
Right, so you have this is W, right?
Mm-hmm.
And
Yeah.
dv dx is negative W.
Mm-hmm.
So you have this. So you're going to 0, and that's correct here because your slope is
0.
and negative. So this is correct.
Okay. Oh, so
And if this is the derivative of this, you're starting positive. So you need to actually keep going up and then curve down like that. So because you're getting more and more negative. So you.
Oh, like up here is positive, like for
So
this.
this is the derivative
Yeah.
of this. So you actually keep going up for a little bit.
Okay.
And then you curve down, and by here you're like going very
Curve down. Oh, because it's very negative.
Yes.
Ah, I see. I swapped them. Oh, I see.
Good job. Yeah.
Oh, okay. I see. I see what you mean. Like that. Okay.
Great. You followed the logic, right? Or
Yes.
the-
Yes. I
You
swapped
do like
it
this.
wrong
Now,
twice.
if you, I just want to know, have you understood? I mean, over and above the review or anything like that.
Mhm.
Why is this? What is happening to the slope of the curve that we have drawn in for M? There is a moment diagram.
Yeah.
You've drawn the slope as.
Yep. Yep.
What is
Like I
happening
said.
to the slope?
This it is increasingly downward. So then
No, it
this
is not down. I want you to be quantitative. It is decreasing, increasing, likewise.
the slope is increasing,
Increasingly decreasing.
increasingly decreasing.
First of all, is the slope positive or negative?
The slope is negative.
Yeah. So then increasing, decreasing has different meanings. So you have to be a little careful.
Oh, I guess it's decreasing. It's increasingly decreasing, which is decreasing. Yeah. So then this is more negative here.
Okay.
And same thing from that to
Yeah,
that.
from there to there.
Yeah, the logic. Got it, right?
Yes.
And also he was pointing out that there it is 0, here it is, when it's going down, it's infinite.
Yeah.
So, right?
Yeah. Yeah.
So
Yeah.
that-
This is
So
this
that's
is infinite.
the maximum. that he was trying
Right.
to
Right.
point
That's why I said this is infinite.
Okay.
Yeah. I think I should have probably. It would be more intuitive if I drew. Yeah. Okay. I
You have derived everything on the right hand side.
yeah.
You are not correlating it. That's all. I mean, probably you are a little anxious also. I can feel you're taking a little bit. You're
Yeah.
a bit anxious. Remove the anxiety, you will get into it.
See, it's the reason why that's infinite slope
Mm-hmm.
is again can be shown from this.
Mm-hmm.
Because your slope is given by W.
Yes.
And there, W is just starting,
Yeah,
but there is also concentrated load P.
Yes.
Any concentrated load is like W infinity.
Yeah.
Because it's over a zero.
Zero
uh,
change in
exactly,
Yeah.
exactly.
Okay.
So whatever the value, it's infinite. And that's
Right.
why
That's why
you
I had a
have
vertical
a
line.
drop
Yes.
or increase depending on the sign of P.
Okay. Yeah.
You will have either an increase or
Yeah.
decrease, which essentially means infinite slope.
Mm-hmm.
So this equation works even with not just with distributed loads, but even concentrated loads.
Yeah. Okay.
Whenever concentrated loads are there, this will tend to infinity.
Yeah, I
Which means
see.
a vertical line.
I see.
And the length of that vertical line will be same as the force that is there at that point.
Yeah. Okay. Okay. I think I spent enough time up here.
Good.
I think that was
It's
enough.
worth it. All of us learned.
Good.
Oh yeah. So good. Thank you. Oh, here's my first one.
You're your password.
Okay. I did 5.4-6. So mine, mine dealt with what you call it, the normal strain of the bar.
4.5.15.
No. That is old. No. He corrected. I had sent a mail regarding this also. That's why I asked you whether you have updated or not.
I'm good.
He has updated the rest of the problems also. You make sure everything else is also corrected accordingly.
So there's a bar on a hinge, and then there's another part that's on rollers. It has the force P applied at both ends at distance A. And the distance here is L. The thickness is given as H. And then it gives the displacement from the bending moment already. So the length equals 1,750 millimeters. Thickness equals 140 millimeters. And the displacement is 2.5 millimeters. One of the key assumptions is that this value is significantly smaller when compared to the total length of the bar. So it lets me neglect like extra terms in my equations when calculating the radius of curvature. So for part A, I need to figure out what's the maximum strain E at the top and bottom of the bar. So first thing I need to do is calculate the radius of curvature, which is given L squared over 8. And then, so my equation for the strain is H over 2 times this. And if I plug this in, over 2 L squared. And that simplifies down. Plugging in all the values that it already gave me, you get 4, 140 millimeters, 2.5 millimeters over 7 meters squared. This comes out to equal 0.00457, and it's unitless for the normal strain. And well, I think I did it wrong. So, oh yeah, this is just the normal strain, and it's unitless because the millimeters, they cancel out. Millimeter squared cancel out. And so then part B asks if the allowable strain was 0.006 and the deflection cannot exceed 4.3 millimeters, then what's the maximum length that the bar can be, which is the L value here. So the allowable is 0.0006, and the max deflection is 4.3 millimeters. I can use the equation that I already derived earlier to calculate this over L squared, and then rearranging it to equal L. It's L squared equals 4H over E. Then plugging in values, I can cancel this and move it over. Square root 4H over E equals square root of 140 millimeters, 4.3 millimeters over 0.0006. This comes out to equal L equals 2003.3 millimeters. And one of the good things about this problem is that I didn't have to calculate any of like the deflection or anything because it already gave it to me. So even though it listed the P values and it gave me like the distances of A, I didn't have to calculate the moments or anything because it already gave me it. So I could just kind of skip all those steps. And another big assumption also that relates to radius of curvature is that this follows like a perfectly circular arc all the way around. And that's pure bending. So that's
Okay. There are a few things that I just like you to keep in mind. See, the way you have drawn this force P, there will be
Oh, I meant to. Yeah, I understand.
so an axial load and vertical load. Okay. Because see, as the beam curves, the load remains vertical.
Yes, sir.
Unlike, for example, if you have a aircraft, you have an engine, a jet engine, let's say, most of the thrust is coming from the nozzle, okay, and it is along the axis of the nozzle, right? So there, if I have thrust vectoring, for example, in some fighter aircraft, I can change the direction of the nozzle. When I change the direction of the nozzle, what happens is the direction of the force also changes because the thrust will now be along the new axis of the nozzle, right? So in such situations, you have non-conservative kind of a system.
Okay.
So in other words, energy gets dissipated. So you have to be a little careful, like
When drawing,
even when the beam bends, that force
Is
P
still
remains vertical.
Okay.
So only then most of the things that you have done here are valid.
Okay.
Okay. So the other thing is these equations that you have here, this one and also this one, I want to understand how these are derived.
So the radius of curvature is like L is 1 squared. I don't know if it's +1. I know it's the squared values. And I was watching a YouTube video explaining it, and it was talking about because the like relative deflection is so much smaller by like orders of magnitude, like 3 orders of magnitude, that you can neglect a lot of terms whenever you're calculating the radius of curvature. I don't know the exact derivation.
Okay, so if you remember in one of the earlier classes, we had derived this. Remember this? Yeah, so just like we had a force is equal to EA times du by dx in a bar, and you had the torque in a shaft equal to GJ times d phi by dx, which is a twist per unit length. We had derived this in terms of the curvature. Okay. So now this delta that you have is nothing but W at x is, if I start x from here, right? So at x is equal to A plus L by 2, right?
Okay.
So if you have this, now you know the bending moment in this particular case, right? As if you can get M as a function of x, EI is constant because it's the entire beam is made out of the same material and it's having the same cross section throughout. So EI is a constant. So as soon as you have a bending moment diagram for this, there is M as a function of x. You can integrate this twice.
Okay.
And then you will get an expression for W as a function of x. Right? So when you get W as a function of x, all that you have to substitute it x equal to A plus L by 2 to get your delta. Then you will be able to show what delta is in terms of all these P, L, and A. P and L will enter through this because the moment depends upon what your P is. Right? So for this, you just have essentially you have a support load over here, and you have your E over here, right? And the area in which you're interested, you don't need to get even the bending moment diagram for the entire beam because I am only interested in the delta, and the delta is coming at the center. So if I divide the beam into 3 portions, I need the bending moment only in this portion, right?
Okay.
Can you get the bending moment in this portion so that you can substitute this and into this and integrate twice?
Probably not, but I can try.
Okay, so just look at what these forces are.
So just like relative to the middle, the moment will go this
What
way.
would the reactions be? It's a symmetric problem.
That.
you utilize the symmetry.
So confused. Is a reaction? Is like that? Is that what we're talking about?
Okay.
That's just like relative to the middle here. That's the moments.
Now, what we want it as a function of x, because we need to integrate with respect to x. After integrating, then we can substitute x as a plus L by 2. We cannot substitute it upfront.
Okay. Just px plus.
But you can determine your F R, the reaction forces, right?
Just be. I'm just saying, because this is minus that. I'm confused. It's on the other side. That's also x displacement here.
No, you have to draw a free body diagram only
Only half.
where you want to plot. So not don't take the L by 2, take some value of x. So take the length of the beam from the left end to a distance a plus x, right? Where eventually you want to set x equal to L by 2, right? Or if you want to start x right from the left end, then it will
Just
be
like that.
yeah. So where are you starting x from?
I'm starting x from the left hand side here.
Okay.
Oh, so earlier were you saying that x is the middle point?
Yeah.
X is the middle.
That's where delta is defined, right?
Okay. So just be x minus L over 2, because if this distance is x, you're starting it here. X FR, yeah, x minus a, just like this. Okay.
But you can determine FR in terms of P by summation Fy equal to 0.
In terms of t,
P.
p.
Yeah, because summation Fy equal to 0, right?
Yeah. Okay. So f
For the whole beam.
is just equal to p of x like that. Is that what you're saying?
So that's the. No, see,
This
Fr
is
is
equal
a,
to 0. It cancels.
see, Fr is the force which is coming through the hinge, right? So what you're writing there is Fr into x minus a. Is that what you've written?
X minus a.
That's a moment. No, in the other equation.
Here.
Yeah.
Yes. Because the moment summed is 0 because it's at equilibrium.
Yeah, but there's one more equilibrium equation, which is the summation of forces in the vertical direction.
Oh, like Fy equals 2 Fr minus 2p.
Correct.
Okay.
So Fr equal to.
Is equals to 0 because it's at equilibrium.
So what is Fr equal to?
Fr equals p.
Correct.
Okay.
So now if you just look at the beam, the whole beam, you are having P and minus P separated by a certain distance. So what is it equivalent to?
P just x minus a equals p of x.
No, you just look at this beam. You have already found out these two reactions to be P each.
Okay.
Right? because from the summation Fy equal to 0 equation, we found out that these two forces are P, right? So now if you look at this, there is a force acting downward, there's a force acting upward. Both are equal in magnitude and separated by a distance. What is that equivalent to?
It's separated by distance A.
Yeah. So what is it equivalent to? Instead of two forces acting at equal and opposite at a certain distance, what can that be considered to be equivalent to?
Like just a force like in the middle,
Yeah.
acting down based on like the relative
Yeah.
distance.
So that is down. Similarly, you have this up, right? So what is that equivalent?
0.
Forces are 0, but
Yeah.
what is the resultant of that? Other than forces, there are
Moments.
yeah.
Moments. It would just
So
be.
what is the moment there? It's like a moment that you're applying, right? There's,
Oh, the moments go in the same direction.
correct.
Okay.
Yeah. So this is equivalent to applying a end moment there. That's all.
Okay.
Okay. If you think of the entire beam, not just going all the way up to A here,
Okay.
but stopping here,
Okay.
you can think of it as two moments which are applied.
Mm.
Because that moment is equal to P times A. So a moment P times A is applied here, and a moment P times A is applied here, and the beam length is only this much. Okay? So in that case, can you think of what is actually happening in between now? What would be the bending moment diagram in between?
Moment equals. Well, the bending moment diagram, it would just be like this way and this way. PAH. No, that's moment. Like that.
Can you draw a free body diagram of just the
Yes.
portion of the beam between the supports?
So you'd have P of A.
Now we have replaced P and FR with just a moment.
Okay. Goes this way.
That moment is equal to P times A. Yes. This is the simplest bending problem that we started with. Remember? Pure bending. So it's a beam with pure bending, right? So bending moment is the same at both the ends. So what is the value it can take in between?
It's just 0?
No. So this is for that portion, right? Now
Yes.
can you draw a free body diagram of just a portion of this beam from the left end onwards?
Okay.
Yeah. So that's PA. So what would be the reaction of the material at that cross section where you're making a cut?
It would bend that
Very
way.
good. Yeah. So that is nothing but your bending moment.
Okay.
So your bending moment is equal to?
Equal to the distance here, which is L over 2, and then has to cancel out P over A. So
See, this is not a force to get a moment. It's a moment itself.
okay.
PA is a moment. So it has to be contracted by another PA there. And P is a constant, A is a constant.
So it'd still be PA right here?
Yeah.
Okay.
So wherever you cut in between those two hinges,
It would. So it's just PA the entire time.
yeah, everywhere it's PA.
Okay.
So if you draw the bending moment diagram, it will be a constant. So it'll just be a rectangular shape. You understand? So now you have a constant value PA there. Now I've written an equation in red on the top right corner. You replace M with PA. So in this equation, P is a constant, A is a constant, E is a constant, I is a constant.
Like that. It's just A equals.
Yeah. So
Okay.
if you integrate that twice, what happens?
Am I integrating with respect to A?
Yeah.
So it's just
Integrating with respect to x.
X.
A dx square is equal to d square w. Integrate.
You can write it the other way around. You put the a on the right hand side. That constant a is nothing but PA divided by EI. How are you cancelling P and EI?
I thought you said that they're. Oh.
Very good. Yeah.
Okay.
So it's some constant. Okay.
Hmm.
Everything on the right hand side is a constant.
Hmm.
So when you integrate this equation, what will you get? dw by dx equal to
Times integrating with respect to X is just X.
very good and plus
Plus.
no, you'll get an
Oh,
integration.
plus C,
constant.
plus C, plus C, plus C. C1.
Okay, you can integrate it once more.
So this is W equals PAEI times X squared over 2 plus C1 X plus C2.
Very good. Yeah. So
Okay.
you can. Is it possible to determine C1 and C2?
Look at the diagram now.
Is because it's equal to this. I don't know.
So what is W? W is the deflection.
Hmm.
So it's the downward deflection.
Okay.
Correct? So you look at the support, what kind of support do you have?
The support here and here.
Yeah.
Okay.
Will it allow it to move down or up? Because it's hinged.
Yeah.
Will it allow to move up or down?
No.
It won't,
I
right?
won't allow it to move.
So
Just
your
zero?
W has to be equal to 0 at the hinges.
Okay.
But that is for a particular value of X.
Okay.
What values of X are at the hinges?
X minus L over 2. If this distance is X, that's L over 2. PA. PA? What?
Make things simple. Just leave out the ends beyond the hinges. Okay.
Okay.
Just draw a beam of length L from hinge to hinge, right?
Mhm.
And now you start your X from the one of the hinges,
Okay.
left hinge. Yeah, you can start X. So X varies from 0 to L,
Yep.
and your delta is at L by 2.
Mhm.
Okay. So I want to eventually what I want to get is an expression for delta. See, I've asked you to prove this, right?
Mhm.
That's nothing but equivalent to saying delta is equal to L squared by 8P or whatever, right? So it's essentially a relationship between them, right? So to get that, now you have an expression for W throughout the length of the beam, throughout this length,
Mhm.
right? Now what you want to do is,
Say X is L over 2.
but it isn't still in terms of two unknown entities,
Okay.
this C1 and C2. So to determine C1 and C2, I can apply the fact that W equal to 0 at X equal to 0, W equal to 0 at X equal to L.
Okay. So when X is 0, 0, and then
W of 0 equal to 0, W of L equal to 0.
associate 0 equals PA over EI times L squared over squared plus C1 plus C2. Like that? Is that what I'm meant to do?
Okay.
And I can plug in the other initial condition where that's 0, that's 0. So that means that C2
Very
equals
good, yeah.
0.
Yeah.
So that means that C1 is equal to PA EI.
It's not C1 or L, it is L. Sorry, not C.
C1 into L.
Sorry.
To then you divide by L. So cancels. So C1 equals PA EI L over 2. So the final equation is W is equal to PA EI times x squared over 2 plus PA over EI L over 2 times L, not times L. Take that. You can factor that out. So PA over EI x squared over 2.
Okay, so now can you determine delta? What is the relation between delta and W?
Delta.
Delta is same as W at a particular value of, yeah.
So equals.
So at that time I was starting X from the left end, but now it's just L by 2. Okay.
PA over EI times.
It's L by 2, not just A, not A.
So it's L by 2 now? L by 2 squared over 2 plus L over 2. Like that? You just write it out?
Seems to be something wrong because you can't add a square of a length and a length.
He is not substituted for X. He's kept XS. He's supposed to put L instead of X.
Correct.
So he's kept L like at the bottom. You don't get X. You get everything in terms of L.
C1 L equals negative PA EI all squared over 2. EI. So I'm not supposed to have X here whenever I rewrite it like that? Okay. Plus EA over EI all over 2 is equal to EA over EI.
So you have C1X, right? The term, second term there.
Yeah.
C1 into X.
Mm-hmm.
Have you substituted for X also?
Yeah, I said whenever X equals L, it's equal to 0.
Okay, that is for calculating your C1. So you have already found C1.
What is C1? Write the expression for C1.
There, yes, written.
Equals PA. Don't we rewrite that to be X? Is that what I'm supposed to do?
Something is wrong. See this term is C1 times F, right? C1 times F. X.
Mhm.
I Are you writing both there?
Yeah, so it's C1 times L. Then I solve for C1 because it's
No,
equal
no,
to
that is to solve for C1. You already got C1.
yeah, which is this.
Yeah.
And then I put
Now-
that here.
Yeah, you have to put the
Oh, I still need the L. Oh,
you need the X, C1 times X. See, the full expression for W when you write, you will have C1 times X, which will be L into X by 2. What you have got here is correct.
okay.
So you've got substituted the values of the boundary
Mhm.
conditions. You've calculated what C1 is.
Okay.
Now you go back to the equation
Original.
for W. You can substitute C2 equal to 0, C1 equal to this.
Yes.
And then you have an expression for the deflection anywhere along the length.
So I was just missing the X term here. Okay.
Okay, so that's for any X.
Mhm.
But you are interested in delta. And delta is at X equal to L by 2.
L by 2. Over 2 minus L over 2. Over 2. So minus me. Square. Over 2. So it's P A E over I L squared over 2 minus L squared, which is P A over E I negative L squared over 2 is equal to W. Because L times L is L squared. L squared over 2 is just L squared.
So now this makes sense because your delta is proportional to P. The larger the P, the larger your delta, right?
Hmm.
Your expression shows that. And larger the length, larger the delta. Just imagine the same load you're applying for a much larger beam, you will get much larger delta, the deflection there at the center, right? And what about EI, which is the bending stiffness? So you have a stiffer material, larger E, you'll have lesser delta.
Lesser delta, yeah.
And if you have a cross section, which is like an I section, for example, your second moment of area I will be larger. So if it is larger, then your delta will be smaller. So it's all intuitive, right? Whereas the equation that you started off with, P and delta are inversely proportional. It says that if I increase P or if I increase delta, the other one will go down. So there seems to be something wrong with that.
This is the radius of curvature. It's not the P force. It's like
Okay.
rho.
Oh, that's rho.
Yeah.
Okay.
Yeah.
So how have you calculated that rho there, the radius of curvature?
I watched a YouTube video explaining how to calculate it if you have a small displacement relative to the total length. It was describing the problem.
2.5 mm is the deflection at the midpoint, not the curvature, right?
Mhm.
Okay.
The deflection relative to the total length is really small, so you really use a simplified term.
Okay, fine, fair enough. So now what you're having there is not even the curvature, it's the radius of curvature, I think. Yeah, because it has the units of length.
Yes, sir.
Numerator is distance squared and denominator is distance. So it should have the unit of distance, which is the radius of curvature. Right? So now how are you getting that radius of curvature to do the calculation? So that's what you're substituting as L squared by 8 delta, is it? Yeah, to get to your strain. Okay, fine. Fine, I got you, yeah. No, the confusion was because you're written
it looks like a P?
Rho like P, that's why I was
okay.
That's fine.
Okay.
Then what about the second part? Can you explain that, the logic behind that, what you have there, the boxed expression, what I had boxed in red?
Equals times H over 2, like EI. And so, H. I originally just got it from here, from this relation, with the radius of curvature relating it to it. And so then you eventually just get that. But do you want me to, like...
Okay, I got you, yeah. So it's the same thing.
I just like reuse the equation.
Okay. So actually this is not something that you need to actually remember and write, because see what we have is already this general equation. In this d squared w by dx squared is nothing but curvature, which is 1 divided by radius of curvature. So what you're calling as rho there, this thing is nothing but 1 by rho.
Okay.
So m is equal to ei divided by rho. So from that rho, you can actually calculate rho equal to ei divided by m.
Okay, so in the future, you want me to show like the derivation from the main equation?
Correct. So it's all kind of equivalent.
Okay, that makes sense. I'll do that.
Sure. So when you submit your handwritten thing, that time you can include all of this and substitute. You can probably take
I'll take a photo.
Picture. Anything else you want to add?
He was trying to hold it. The first thing you said, no? You hold it, you can hold it like this only.
Okay.
I had problem 4.3 left hand. So basically, we have to start playing under the conditions. The still just loaded on the game has this kind of variation. So we basically want to find the surplus speed and 4 meters from this thing. So they give us this diagram, and what we're worried about is 4 meters of typical length. So since our total length is 6.2 meters. That's the same as 2 meters from the wing. So we had successfully written our cut at 2 meters from the wing. So that so we started at 0, 9, and we're to this full continuing obviously.
I have a microphone.
Sorry.
Oh, very good.
All right, and
Can
then
you repeat a few?
oh yeah. So we have this airplane under cruising conditions, and we have this diagram that shows the load acting on the wing, the idealized load variation that's shown in this figure of the loads on the wing, and we want to find the shear force V and the bending moment M at 4 meters from the tip of the wing, which is the same thing as 2.2 meters from the root of the wing. So basically, I made a cut at 2.2 meters from the root of the wing, and that's the diagram that I'm showing here. And so what we're finding is our shear force V, and this load will create a positive moment. So we're going to have a negative, or this way, negative bending moment M that we're trying to solve for. So we're assuming that we're under equilibrium and that this is a 1D beam. So we're going to first use sigma F in the y direction. I also have our coordinate axes, just x and y. So this is equal to 0. So 0 is equal to what we're trying to solve for, which is going downwards, so our negative shear force. And then basically just taking the integral of our load here. So first we're going to solve for this kind of this like triangle here. So we're going to add 1/2 times 900, and I actually forgot to write distances. So this is 1 meter. This to here is 2.6 meters, and from here to here is, I believe, 0.4 meters. So it's 1/2 times, for this first triangle area, 1/2 times 900 times just 1 meter. This 900 is divided by meters. So that's a triangle. And then we have kind of this rectangle here for this 900 Newton meters. So that's going to be 900 times 2.6, I believe. Unless I screwed something up here. Yes, 900 times. Well, it would be 900 times 3, actually. And then we need to find this little triangle region right up here. So that's going to be 1/2 times. We need to solve for what is this value up here. So that's going to be 900 plus Newton meters. I forgot units. This is Newton meters, and this is meters. That's 900 plus. We're going over 0.4 times. Since we know we're going up to 1600, that's a difference of 700, so our slope is 700, and that is over 2.6 meters. This is meters. This is 5 meters. And then we want to find what is the difference between 900 and that value that we're trying to find. So minus 900 Newton meters. And then that is over a distance of 0.4 meters. So when we solve this out for V, we get that V is equal to 3,171 newtons, which is equal to 3.17 kilonewtons, and that's going downward. So that is our V. And then we also want to find M. So same thing, we're in equilibrium, so we're going to do sigma M, which is equal to 0. So 0 is equal to our moment that we're trying to find, which is a negative moment. And then just the same thing, except this time we're finding the moments from each, from the entire load. So we're going to start with this triangle, so 1/2 times 900.
The second term for the shear force, the last line that you have for the shear force. See, this portion is actually made up of 2 portions, right? So it's a rectangle.
Yeah,
it's a triangle.
I
So
included
it's
this as like one big rectangle.
Oh, okay, okay.
And
So
made
the
it
first
three.
time you did it,
Yeah.
you made it all the way up to here.
Yeah.
Oh,
So we have finding a moment from just this triangle. So 1/2 times 900 meters. Again, times 1 meter. But then since it's a triangle, we want just like 1/3 of the way into that, like the bigger region of that triangle. So our distance is going to be 3 plus 1/3. So 3 meters plus 1/3 meters. And then our next region is going to be this entire rectangle. So that's going to be 900 Newton meters times over a distance of 3 meters, and then just the middle of centroid of that rectangle, which is just 1.5 meters. And then finally, we want that triangle up there. So the same thing from up here to figure out the area of that region. So it's going to be 1/2 times 900 plus 0.4 times 700 over 2.6 minus 900. And then again times 0.4. And then since when you find the centroid, again, it's a triangle, we're just going to go 0.4 meters and then 1/3 of the way divided by 3. So then when we solve for m, we get that m is equal to 5,552 newtons, which is the same thing as 5.55 kilonewtons, and this is clockwise, or like a negative moment.
unit of moment is?
A kilon meters. Yes. Yes.
Which are values are okay. Anybody any questions for Vikrant?
Good.
Thank you.